Often we'll be interested in data that are better characterized using a proportion rather than a mean. And so we might be thinking about the proportion of successes that happen, or the proportion of individuals that support a particular candidate, or the proportion of time that something happens. But in all of these cases, we're not thinking about the mean as much as we're thinking about this proportion, about how much of the total is classified in some particular way. And in these settings, we need sort of specific methods to address the proportions that might not apply directly to the means. So if we're interested in population proportions, then the key idea is that proportions are tied to the binomial distribution. And fortunately for us, the binomial distribution can be well approximated using the normal distribution. And so if we want a confidence interval for a particular proportion from some population, then what we can do is we can say, well, the binomial can be approximated by the normal, and the normal can be used to construct confidence intervals. And so we can get approximate confidence intervals through the procedure of using the normal-based approximation. So what is the normal approximation to the binomial? Well, if x follows a binomial NP distribution, then x is counting the number of successes in n independent trials, where each trial has a probability of success of p. So we can think about this as flipping a coin, right? So if we're going to flip a coin 10 times, each time there's a 50-50 chance that it comes up heads or tails, then this would be a binomial 10.5, right? If there's 50 flips of a coin, then it would be a binomial 50.5, right? And all we're doing with that coin flip is we're counting how many times did we actually see the heads, or how many times did we see the tails, right? It doesn't have to be a 50-50 chance. It can be any success probability. We capture that with the parameter p. And the parameter p is really the parameter that we're most interested in. We want to know what proportion of the time are we successful, where success can mean sort of whatever it means based on context. In the case of the binomial, we have that the expected value is always going to be n times p, and the variance is always going to be n times p times 1 minus p. Right? Now, if n is large enough, and large enough in comparison to p and 1 minus p, then we know that x is going to be approximately normally distributed, right? And so normally what we think about is that n times p has to be greater than or equal to 5, and n times 1 minus p also has to be greater than or equal to 5. But this is just a rough rule of thumb, right? Sometimes we're going to require it to be higher, sometimes we would require it to be a little bit lower. You know, it depends on the context and how good enough approximation we actually need. But in this setting, right, we require this type of approximation here. But with this approximation, we can then say that x is going to follow something that looks like a normal distribution, right? And in particular, x is going to follow a normal distribution that is n times p for the mean and n times p times 1 minus p for the variance. And so specifically, we're thinking about the fact that the expected value is np, and so then the approximate mean is going to be n times p, and then n times p times 1 minus p for the actual variance, and so then in the approximation, the variance is the same thing, right? So we just are literally taking what is the real expected value, plugging that into our approximation, same thing with the variance there. Now, the sample proportion, which we'll denote using p hat, is always given by x divided by n, right? So the proportion of time that something happens is x, which gives us the number of individuals in our sample, or the number of observations in the sample where it happens, right? So x is counting the number of times it occurs, whatever it is, right? So I'll throw those in quotes there. It occurs in the sample. And so then if you want to know the proportion, well, that's given by x divided by n, right? The number of times it happens out of the total number of times that it could have happened. That's going to be our proportion. And so our estimated proportion is x divided by n. And x divided by n is going to have an approximately normal sampling distribution, because the normal, anytime we multiply it by a constant, remains normal. And so specifically what we're going to see is that x over n is going to be approximately normally distributed. The mean gets multiplied by 1 over n, so that's going to have p as the mean, right? Because n times p divided by n is equal to p. And then if we take n times p times 1 minus p, we have to divide that by n squared, right? And so we'll get n p 1 minus p divided by n squared for the variance, and the n squared will cancel out each other, and we'll get p times 1 minus p over n. So we're going to get an approximate normal distribution for the proportion as well. Right, specifically, p hat is going to be approximately normal with p as the mean, p times 1 minus p over n as the variance. Now, from this point, we can use this result here in order to form normal-based confidence intervals, right? Because we know that p hat follows this approximately normal distribution, so we could standardize it and then find confidence intervals from there. So in particular, we could think about the fact that, say, p hat minus p, divide that by the square root of the variance here, right? So that's going to be p 1 minus p over n, right? The standardized is going to be about a normal 0, 1. And so then at this point, this term right here is going to be an approximately standard normal, which means that we can use this as the basis for normal-based confidence intervals. So to actually form these, right, we're going to take the critical values at alpha over 2 to be the standard normal critical values at the alpha over 2 level, which is to say that if we take phi, we plug z alpha over 2 into it, that gives us alpha over 2. Again, phi is going to be the cumulative distribution function for the standard normal distribution. Then the two-sided confidence interval is going to be p hat plus or minus our critical value times by the standard error there, right? And the standard error is given by p times 1 minus p over n. We don't know what the real value of p is, and so in place of the real value of p, we replace that with p hat here, right? So these are going to be the estimated values for this, right? But this is simply following from that result that we had on the previous slide about the normality of this, right? And so this is essentially just the same normal-based, z-based confidence intervals that could be derived for the mean in a normal population. But here, we're basing this all off of the approximation of the normal to the binomial. And so it's going to take approximately the same form as any of the mean-based confidence intervals. Okay. Now, this is only going to be an approximate interval. And again, it's most appropriate when n is large. The larger the n, the more appropriate this is going to be. Okay. Sometimes we want to be sort of more conservative in our approach here, and one way that we can do this is by considering what value of p hat we plug in to the standard error, right? And so this p hat, that's our point estimate. We'll always just keep that as p hat. But then over here we have the standard error, right? And if we're not very certain that we have the right point estimate, then it's possible that p hat times 1 minus p hat is quite far away from the truth. And so what we can do instead is we can plug in 0.5 into this case, right? So that's 0.5 times 1 minus 0.5, which if we simplify it down, we get p hat plus or minus our critical value times 0.5 over the square root of n. And what we are doing with this is that it turns out that if we want to make this standard error as big as it can possibly be, right, then we make it as big as we possibly can by plugging in a value of 0.5. And the reason we want to make this as big as we can is because the bigger this term is, the wider the confidence interval is going to be, and the wider the confidence interval is going to be, the more conservative we're being with our confidence interval, right? And so if we want to be quite conservative with this, if we want to make sure that we're not going to have it be too narrow, because again, it is only an approximate interval, right? We could still get things wrong. And so if we want to be conservative in our approach, then we take 0.5 into the standard error over here, and then that's going to give us the widest possible confidence interval for the proportion here. And that's going to sort of rectify this approximation if we're worried at all about it. So to see an example of this, we can look at this marketing team from a tech company, and they want to estimate the proportion of customers who are satisfied with their recent product launch. They take a sample of 1,024 customers and find that 800 of those customers that are surveyed are satisfied. And they want a 99% confidence interval for the proportion of satisfied customers. So in this case, right, we have a large n, right? So n is large. And so using the approximation is going to be totally fine. And so then in this case, what we want to do is we want to pull out sort of the key pieces of information, right? So x is going to be 800, n is going to be 1,024. Okay. And the other piece that we need is our alpha. Alpha is going to be 1 minus 0.99, which is 0.01, right? And so then we're going to want the critical value corresponding to z of alpha over 2, right? In this case, that's z of 0.005, right? And we can grab this from, say, the statistical programming language or similar. Okay? And so with this information pulled out, we can actually start constructing this confidence interval here. And so we can see how to do this. So because the population is large, the normal approximation is going to apply. We can take x to be 800 and 1024. P hat is going to be 800 over 1024, which gives us 0.78125. The alpha, as we discussed, require z alpha over 2 of z of 0.005, right? This is 2.58. Again, we can get this using R, using this Q norm function, right? We plug in 0.005 because we want z of 0.005 here. Okay. So with all of this information, we turn to our confidence interval formula. We take our estimated proportion plus or minus the critical value times the standard error here, right? The standard error is going to be p hat 1 minus p hat over n, all square rooted. So then we can plug in all of the values here, right? P hat's 0.78125, plug that in the 3 spots we need it, plug in n is 1024, right? And we work out that the interval is going to give us 0.748 up to 0.815. Right, so this is going to be a 99% confidence interval based on the normal approximation. So this is an approximate confidence interval. Now, as a follow-on to this, the company maybe did not feel particularly confident that the 800 out of 1024 is a good representation of the truth, right? And if this is the case, they might want to be more conservative in their 99% confidence interval. So here they want to find a 99% confidence interval, except they want to be as conservative as possible. Now, the thing to note in this case, right, is that we don't actually need to change a whole lot of anything that we were doing, except when we're going to be taking this root of p hat 1 minus p hat over n, right? We're going to replace this by square root of 0.5 times 1 minus 0.5 over n, which is just 0.5 divided by the square root of n. And by replacing it with this term, we're going to make sure that the interval is actually conservative, right? And so we can go through all of the information's the same as before, right? So we take p hat 0.258, plug in the 0.5 into the standard error instead. This is going to give us, there should be a division in this case here. Right? So we should have this term being 0.5 divided by 1024, or a square root of 1024, right? But either way, it works out to be this interval right here. So from 0.741 to 0.822, okay? And the thing to note in this case is that it's wider than the interval that we found in part A, where the interval we found in part A was 0.748 to 0.815, right? And so if we notice, the lower bound of this new interval, 0.741, is smaller than the lower bound before, and the upper bound at 0.822 is actually higher than the upper bound that we found before, right? And so this interval here is just simply wider than the first interval we found. And so if we're worried about this previous interval, then using 0.5 instead is going to give us a more conservative interval. It's going to allow us to be sort of more certain that we're actually getting that 99% confidence that we want. So using 0.5 in the standard error is always going to create the widest possible interval for any value that we could plug into the standard error there. So if we're dealing with proportions, then the confidence intervals can proceed in much the same way as if we are dealing with means, where what we're really relying on there is that the normal distribution can approximate the binomial distribution. And then we can, after applying that approximation, use normal-based confidence intervals for the proportions. This is going to be quite useful whenever the data happen to be data that are well summarized with a proportion. And the main thing that we have to be careful of is that because this is an approximation, they can be wrong. And so sometimes it's going to make sense to, instead of fitting the direct confidence interval, to fit a more conservative confidence interval where we replace the estimated proportion with 0.5 in the standard error. We don't always need to do this, but if we're worried about our coverage, then that's something that we can do in this situation.